In this lecture, we want to talk about some applications of the sampling distribution of the sample mean, specifically talking about how you use the central limit theorem. So I have two examples that I'm going to work through. The first talking about a 10-minute oil change joint, and then the second one is going to be talking about the length of human pregnancies. So for the first one here, I'm going to, when we get to the second part, problem B here, I'm going to solve this problem by hand using the z-score table. So have that handy. But then for the rest of the problems, in the rest of the parts, I'm actually going to use the TI calculator. Okay, so here's the first problem. Suppose that the mean time for an oil change at a place called a 10-minute oil change joint is actually 11.4 minutes with a standard deviation of 3.2 minutes. Okay, so here's what we know, all right? The mean time is 11.4 minutes, and the standard deviation is 3.2 minutes, okay? Notice what it doesn't say. It doesn't say anything about like the time to change in oil is normally distributed. It just doesn't say that at all, okay? So the first part says, if a random sample of size n is equal to 35 oil changes is selected, describe the sampling distribution of the sample mean. So we're gonna sample 35 oil changes and compute the sample mean from it. So recall that the central limit theorem said as long as the sample size is greater than or equal to 30, the sampling distribution of the sample mean will be normally distributed. So let me help put this in writing here. Because the sample size, which is 35, is greater than 30, the sampling distribution of the sample mean will be normally distributed with, so when something's normally distributed, you can say what its mean is, and we denoted the mean of the sampling distribution of the sample mean as mu sub x bar, and that's equal to the population mean, which is 11.4 minutes, and standard error, which we denoted as sigma x bar, and that's equal to the population standard deviation divided by the square root of n. So you would take 3.2 and divide it by the square root of 35. So at this point, just grab a calculator. So you're going to take 3.2, divide by the square root of 35. I'm going to take this out 4 decimal places, so it's 0.5409. Okay, so I was able to say because the sample size is greater than 30, it's normally distributed, mean, standard deviation. We call it the standard error, though. Now I'm going to ask you a probability question. So this is a lot like the previous section. So when a random sample of 35 oil changes is selected, okay, what is the probability the mean oil change time is less than 10 minutes? Okay, so I'm asking you probably the mean. So I'm going to start by defining a variable. I'm going to let x bar be the sample mean oil change time in a sample of 35 oil changes. And what I want to do is I want to find the probability, look, that this sample mean is less than 10 minutes. Okay, so how would we solve this, right? Well, normally distributed, mean, standard deviation, and I ask you for probability. You're just going to solve it with the normal curve. So what I'm going to do is I'm going to draw the distribution of the sample means. Okay, it should be centered at 11.4 minutes. And I want to be less than 10. So here's 10. and I'm going to shade to the left because I want to be less than 10. So the next thing you would do would be you'd calculate a z-score, right? So a z-score here, in this case, it would be your variable, which is x bar, minus the mean, which is mu sub x bar, divided by the standard deviation, which is sigma x bar. So in this case, it's going to be 10 minus 11.4 divided by this value that I got right here, which is 0.5409. So let's grab our calculator. So we're going to do 10 minus 11.4, close the parentheses, divide by 0.5409. And because this is a z-score, I'm going to round it to 2 decimal places. So this is minus 2.59. Okay, so now this problem just becomes, hey, what's the probability a z-score is less than minus 2.59? Well, at this point, you can go grab the table. Area to the left here, minus 2.5 right here, and 9 all the way in the corner here. So minus 2.59. So the probability is 0.0048. And there you go. So basically, really, the only difference between this and the previous section is when you get to the standard deviation, you're really just dividing it by the square root of n. Okay, that's just like not just how you do this procedurally. Like that's really the only difference in the procedure method of it. There's a lot of theoretical differences, like as we were talking about the sampling distribution and the sample mean, but just from a procedural aspect, you're taking the standard deviation and dividing it by the square root of n. All right, let's do 2 more problems here. Now I'm going to switch to just not using the table anymore, but your calculator. So in a random sample of 35 oil changes, again, what is the probability the mean now is greater than 12 minutes? So I've already defined the variable, so I want to find the probability that x bar here is greater than 12. Okay? So sketching the curve again. You should be at 11.4, and now you want to be greater than 12. So I'm going to shade to the right. So to do this in your calculator, you're going to go back, and in your TI-83 or your TI-84, it's just going to be second function distribution, the normal CDF. Okay? So over here, what you see, you have a lower, an upper, a mean, and a standard deviation are the commands you have to put in. All right, so you start with the lower value. Well, the lower value here is 12 because it's a right-tailed test. The upper, because it's a right-tailed test, you're going to put 9999. The next thing you're going to put in is the mean, which is going to be mu sub x bar, which was 11.4. And then the next thing you're going to put in is the standard deviation, which was sigma x bar, which was 0.5409. So let's go back to our calculators. So in this calculator here, you're going to have to actually put in the commands. You're going to have to go 12, comma, 9999, comma, 11.4, comma, and then 0.5409. Close the parentheses. And you get 0.1337 when I do this, 0.1337. Over here, you'll get the same thing. Just a little bit easier to put in. You get the same value. So it works perfectly with your calculator. I think this is a little bit easier than the z-score formula. Okay. Now let's try this one. What is the probability the mean oil change time is between 10 and 12 minutes? Well, again, you're just going to do the normal CDF. And when you want to be between, this is my lower, this is my upper. The mean was 11.4. The standard deviation is 0.5409. So I'll just do this one in the TI-83. So second function distribution, normal CDF. So this one is going to be 10, comma 12, comma 11.4, comma 0.5409. And this probability is 0.8615. All right. So I hope you see really the only difference between this and last week, again, procedurally, is just you taking the standard deviation and dividing it by the square root of the sample size. All right, let's do one more example. So the length of human pregnancies is approximately normally distributed with a mean of 266 days and a standard deviation of 16 days. So here's what we know. Length of human pregnancies, normally distributed. Okay, mu, the average, is 266 days. The standard deviation is 16 days. What is the probability that a random sample of 16 pregnancies has a mean length greater than 217 days? So I'm asking you the probability that the mean length. So I'm going to define a variable. All right, I'm going to let x bar be equal to the mean length of pregnancies in a sample of 16 pregnancies. All right, and I want to find the probability that that mean is greater than 270 days. Okay. Well, how would I do this? All right. Well, first off, we know that since the length of human pregnancies is normally distributed, all right, the sampling distribution of x bar will also be normal, be normally distributed, with, well, the mean we know is mu sub x bar, and that's equal to the population mean, so it'd be 266, and standard error, sigma x bar, take the population standard deviation divided by the square root of n. Well, that's 16 divided by the square root of 16, which would be 16 divided by 4, which would get you 4. So now the probability is greater than 270. Well, that's normal CDF. Whenever you have a greater than probability, the lower value is this. So it's 270. The upper is going to be 9999. The mean is over here, 266. And the standard deviation is 4. And if it helps, you can even draw it. You know, like it's going to be normally distributed, centered at 266, and I want to be greater than 270. You know, if it helps to see the normal curve, you can do that. So I'll do this problem in the TI-84. So normal CDF. So my lower here is 270. My upper is 9999. 266. Standard deviation was 4. And you got 0.1587 when I round it. Okay, not too bad. Let's try this one next. I'm going to switch it up a little. What is the probability that a random sample now of 20 pregnancies, notice how it's changing, okay, has a mean length greater than 270 days. So now here my x bar is going to be the mean length of pregnancies in a sample of 20 pregnancies. And here I want to find what's the probability that this sample mean is greater than 270. Well, again, we know because the original variable is normally distributed that the sampling distribution of x bar will be normally distributed with the mean here, mu sub x bar is equal to the population mean, which is 266, and the standard error is going to change now. So you can take the population standard deviation divided by the square root of n. So now it's 16 divided by the square root of 20. And here it's going to be 3.5777. I'll go out 4 decimal places. So the only difference between these problems now is when I go normal CDF, again it's going to be 270 to 9999. The mean is 266, but now the standard deviation, it was 4, but now it's 3.5777. So I'll go to this calculator now. So normal CDF, 270, comma 9999, comma 266, comma 3.5777. And notice it's probably going to get smaller, right? Because the standard error got smaller. So it's 0.1318 when I round it to 4 decimal places. All right, let's just do 2 more quick problems with this. So we're sticking with the sample of 20 pregnancies. What is the probability that that sample mean is less than 260 days? So the mean is 266. I want to be less than 260, so I'm going to shade to the left. So this is going to be the normal CDF. So left-tailed test, the lower is going to be minus 999 to 260 to 266. And that mean is 3.5777. So normal CDF, minus 99999, 260, 266, 3.5777, and you get 0.0468 when I round it. Okay, last one. Between, what is the probability that a random sample of 20 pregnancies has a mean length between 258 days and 272 days? Well, you know, whenever you have it in between probability, your normal CDF here, the lower is the first value, 258. The upper is the top value, 272, 266. 3.5777, and I'll use this calculator. So 258, comma 272, comma 266, comma 3.5777, close the parentheses, and you get 0.9406 when I round it. All right, class. So remember, just procedurally, the only difference really is this compared to the previous section is you're dividing the standard deviation by the square root of n, and that gets you the standard error of the sampling distribution of the sample mean.